So can you hear me? Okay. You're going to stay here while I talk?
No.
You really want to?
I wanted to make sure that
You want to make sure I'm all right. Okay. Thank you very much, Attilio. It's such a pleasure to be here. After those effusive introductions, I'm embarrassed to stand up. But thank you very much to all of you for your great kindness and for the hospitality that I've been shown. And it's so wonderful to be here in Torino. My story began in 1979 when Carl Sagan, the astrophysicist who created the television series Cosmos, telephoned me and said, there's a woman named Linda Obst who is the producer of the foreign language version of Cosmos who wants to have a blind date with you. She wants to take you to the world premiere of Cosmos as her date, and would you be willing to do that? Well, I was single, so I didn't have to ask my wife's permission, though my wife, whom I married subsequently, has now become a very close friend of Linda's. So we went to this wonderful event, and we became close friends. Our romance never developed. I think I was too much of a geek, as we say, for her, and she was too intense for me. But it was a combination which led, in the end, to Interstellar. Linda telephoned me in 2004, late 2004, and said, would you like to brainstorm, or I guess 2005, October 2005. Asked me, would you like to brainstorm with me for a science fiction movie? I thought for a few milliseconds and said yes, because I saw this immediately as an opportunity to reach, with inspiration about science, to reach a much broader set of people than I had ever done before. And in the end, in fact, we reached 100 million people. How else can a theoretical physicist communicate to 100 million people except by a movie such as Interstellar? And so we sat down and we put together a treatment for the movie. That's a description, in our case, of the science in the movie. That's the most important part. But we also had a story and some characters. And the key thing about the treatment was that real science would be embedded into the movie from the very beginning. And this was the beginning of Interstellar. Linda then brought on, she's a very powerful, she had become by then a very powerful producer. She had done Contact with Carl Sagan. She had produced Fisher King, Sleepless in Seattle, How to Lose a Guy in 10 Days. She's very versatile. And so she brought on Steven Spielberg as the director. And at our first meeting, I said to Steven, I would like to do a movie with you that followed these guidelines, that nothing in the film will violate firmly established laws of physics or our firmly established knowledge of the universe, and that speculations about poorly understood physical laws in the universe, they will arise from real science and not just from the imagination of a screenwriter. And Steven said, yes, I would like to do a movie of that sort. Let's try to make this movie be of just that type. And so I was thrilled, and I found that he was a wonderful person to work with, highly creative, and quite inspirational to work with. Then Linda and Steven worked for about a year to find the right screenwriter. They interviewed a large number of potential screenwriters when they finally settled on a young man named Jonathan or Jonah Nolan, who had only written 3 screenplays in his life, all of them for his brother Christopher Nolan. And so this was his first attempt to be independent of his brother in working on a movie. And so he came on board and he brought with himself some wonderful new ideas that completely changed the beginning of the movie. And I fed to him a number of science books. He was not a scientist, didn't have much training in science, but very bright. He learned quickly. And he spent many months spending a lot of his time reading the books about the relevant science. And then he brainstormed with me about the science in the movie through 3 drafts of the screenplay, and a lot of new science was introduced into the movie through that brainstorming. 2008 to 2010. And then on June 8th, 2010, Steven Spielberg dropped out. I don't know fully why, a number of different factors, but in the end, we had lost our wonderful director. And so the movie stopped, because this would be a very expensive movie, and the studio, Paramount Pictures, was not willing to entrust this movie with anybody except the top director whom they thought were confident could make money for the studio. And so for 2.5 years it was stopped. However, Jonathan Nolan's brother, Christopher Nolan, said to us, even before Spielberg dropped out, if Spielberg leaves, I would be interested in working on this movie with you. But he refused to negotiate with Paramount until he completed his then current movie, Batman: The Dark Knight Rises. And a few months after he completed that movie, he began negotiations, and they took quite a while. But finally, in December 2012, Christopher Nolan signed on as director with his wife, Emma Thomas, as the lead producer. And we were finally starting to move once again. And so I then told Christopher Nolan at our first meeting about this, what my guidelines were about the science. And he said, yes, I like those guidelines so long as they don't get in the way of making a great movie. And then he said, and if you don't like what I do with the science, you don't have to defend me in public. And that made me a little bit nervous, but he was already somewhat nervous. As he told me later, he was afraid that I would become the science police, and I would tell him what he could do and what he could not do. And so our first meeting was a little bit nervous on both sides, but by the second meeting we had learned to understand each other, and it became a wonderful collaboration. We both came to understand we wanted the same thing. We wanted to follow the guidelines, but we wanted to make a great movie, and that we would brainstorm together, as I had done with his brother, toward the goal of a great movie based on real science. And so we brainstormed through 3 more drafts of the screenplay. And by the time he was finished with those 3 more drafts, the movie was changed, the story was changed so much that it had preserved the science vision that Linda and I had from the beginning, but the story and the characters were so different that this was now the Nolan's movie. It was not hardly at all like the story that we had begun with. And so Interstellar really is a Christopher Nolan movie, but with the real science integrated into it very, very deeply as a result of brainstorming with both of the Nolan brothers as well as with Linda Obst. In May of 2013, Christopher Nolan telephoned me and said, I'm going to send a man over to your house to talk about the visual effects, a guy named Paul Franklin. Paul came, we talked for a few hours. He was very smart and very interesting, and then I asked him at the end, what visual effects company you're planning to use? And his answer was, mine. And I didn't know who he was, really. And so I said, what is that? He said, it's called Double Negative. We have 1,000 employees in London and 200 in Singapore. And so after he left, I looked on the internet, and I saw who he was. He had co-founded Double Negative. He was to be the supervisor of visual effects for Interstellar. And he had won the Academy Award for the visual effects in Christopher Nolan's previous movie, Inception. And he went on to win the Academy Award for visual effects in Interstellar, for our Interstellar movie. And his company also won the most recent Academy Award for visual effects for Ex Machina. And so they're a very, very powerful company and wonderful to work with. These are some of the people then that he introduced me to, and I worked hand in hand with them to produce visual effects to visualize black holes and wormholes and astrophysical phenomena in a very tight and wonderful collaboration, particularly Oliver James here, who's standing beside me, I'm holding the Academy Award that we won. He's holding the BAFTA, the British analog of the Academy Award that they won for Interstellar. So now that I've described the people that I worked with on Interstellar, I'm going to let them describe me.
We're still pioneers. We've barely begun. Our greatest accomplishments cannot be behind us, because our destiny lies above us.
The initial impetus for the project had been to say, why not examine real possibilities? Why not actually look at the real science there?
Luckily, we had Kip, and Kip is the foremost authority on all things gravitational.
The warping of space inside here scatters some of it back, glide scattering off of the surface of a rippled ocean. Neither wormholes nor black holes have been depicted in any Hollywood movie in the way that they actually would appear. This is the first time that the depiction began with Einstein's general relativity equations.
The visual effects department under Paul Franklin and everybody at Double Negative took Kip's mathematical data and they created real visual representations of what a black hole is meant to look like.
The collaboration has produced visualization of things which nobody had ever managed to do before. We potentially may have discovered a couple of new things that were lurking there inside the mathematics, inside the physics.
And that mathematics, that is one page out of a technical paper that we wrote about the methods we used. We had to invent a whole new way of producing visualizations because the standard techniques that had been used up until then by astrophysicists and in Hollywood would not produce the quality images that were needed for an IMAX cinema screen when you're working with phenomena near black holes. So we published a long technical paper about a whole new set of methods for doing visualizations, which was one of the outputs of this movie. And then we used it to explore phenomena called gravitational lensing, the computer program that Oliver wrote based on these equations. I also had very interesting conversations with the actors in the film. Matthew McConaughey emailed me just before he started filming, said, can we get together and talk about Interstellar? And we spent a couple of hours together discussing his character, the science in the movie, but also other phenomena like if you have a brainstorm, a great idea in the middle of the night, does it turn out to be any good the next morning? And how do you raise children who are problematic? We just wandered all over the place in a fascinating conversation. Anne Hathaway, we had a great conversation, again, just before she started filming, in which she began by saying, I'm a bit of a physics geek. Can you tell me, is there any observational or experimental data about the laws of quantum gravity? That was the first words out of her mouth when we began our conversation. She turned out to know a lot more science than anybody else on the film except me. And this of one of the women who is labeled in Hollywood magazines the most beautiful woman in the world, but turns out to be brilliant. Michael Caine. I was on set filming with Michael Caine, and the first assistant director who's in charge of the shoot came over and whispered in my ear, Michael would like to have his photograph taken with you. Is that all right? And I was completely surprised that the actor would ask for that. But I said, okay, so this is the photograph that they took. And then an hour later, Michael's wife came and sat down beside me and whispered in my ear, Michael said you were on set, that I should come in and meet you. And I said, well, why? I don't understand this at all. And she told me something that I had not been told by Christopher Nolan, but she said, Christopher Nolan told Michael that the character that Michael plays, which is Professor Brand, is patterned after you. And so I didn't know that, but that's what Chris evidently told to Michael. Jessica Chastain, who plays Michael Caine's, or Professor Brand's daughter, who grows up to become a great theoretical physicist, we worked together on the equations that appear on blackboards and that she is responsible for. And it was really interesting. At the world premiere in Los Angeles of this movie, on the red carpet, talking to the press, the only thing she talked about was what a joy it was to play a theoretical physicist and to work with me on the equations for the movie. So this is my experience with the actors and actresses. Everybody, from the studio executives through the actors, the producers, the director, embraced the idea of embedding real science into this and took joy in making a movie that was involved with real science in this way. So what is the real science? Interstellar is based on an idea that there is a fifth dimension to our universe that we have never ourselves experienced. Normally, we're familiar with the east, west, north, south, up, down, three space dimensions in our universe, and one more dimension, which is time. But in Interstellar, there is then a fifth dimension. It's a space dimension, and it leads out of our universe. So our universe, physicists call this a brane, after membrane. I'm showing only two of our space dimensions, north, south, and east, west. I have removed, in order so that we could be able to comprehend this, I've removed the third dimension, but I'm showing that additional out-back dimension here leading out of our universe. So we think here of our universe as like a flat sheet of paper, and the out-back dimension, the fifth dimension, is going away from there. And the fifth dimension plays a big role in the movie, and you hear the characters frequently talk about the fifth dimension. And it is speculative, but it is a rather speculative but very plausible, quite possibly right aspect of physics, that there really are additional higher dimensions, and that one of them may be macroscopic, big enough that you could go out into it if you were a being that could live in 5 dimensions. So I am going to, in the upper right-hand corner here, I'm going to identify the science that I talk about with an S when this is speculative science, but there's reason to believe it might be true. And a T when it is truth. We are quite sure it is true. There is experimental evidence for it. The theory is deeply understood, and we believe it's quite solid. And that's one of the nice things about Interstellar. It has approximately 50% speculative science and 50% true science. And if you read the book that I've written about the science of Interstellar, you find a detailed discussion of the difference between the two and how speculative science gets disproved or gets converted into true science as we develop a deeper knowledge from experiment or further theoretical work. So wormholes play a big role in Interstellar. This wormhole is truth. It's the wormhole that I knew so well as a child. We had an apple tree behind my home, and my father refused to use insecticides on the apples of the apple tree, so I would be able to just eat them. But they were full of wormholes. And so if this is an apple, it has a wormhole. And this is an ant that lives on the surface of the apple. The surface of the apple is the ant's entire universe. And if the ant is up here and wants to go down there, the ant has a choice of 2 ways to do it. Around the exterior, that's the long way around, or through the wormhole. The surface of the apple is like our universe. It's our brain. It's a piece of our brain, our membrane. The wormhole goes through the interior, which we call the bulk. It's like the 5th dimension. And the ant has a choice of going through the bulk from one place in his universe to the other, or going around through the external universe. And the same thing happens in Interstellar. In Interstellar, we have our solar system, and in particular, the planet Saturn out here. And then we have a distant region of the universe, which is where much of the movie occurs, 10 billion light years distance, very, very far away. It takes 10 billion years for light to travel from one location to the other. So you're not going to travel there with a normal spacecraft. However, in the movie, it is presumed that somehow our universe has been bent around so that if you can go the long way around, or if there is a wormhole, you can go along the surface of this wormhole to get to this far distant region of the universe. And that distance might be a few kilometers through the wormhole, whereas it's 10 billion light years through the external universe. So that's a very fast shortcut through the bulk, through the fifth dimension that is the basis for the movie. Now, to produce the visual images of this wormhole, Eugenie von Tunzelmann was the leader of the artistic team who made paintings of what's on the other side of the wormhole: gas clouds, dust clouds, nebulae, stars, and so forth. I worked out the equations for the propagation of light through the wormhole so that somebody up here by Saturn looking into the wormhole would see what's on the other side. I fed the equations to Oliver James, the chief scientist, and his team, and they produced the images such as this. This is not an image from the movie, but it is an image of that could have appeared in the movie. The difference is that this wormhole, that's the wormhole, you're looking through it, you're seeing some nebulae on the other side of the wormhole. This is close to us, and Saturn is in the distance, and you don't see Saturn and the wormhole together in the movie, but you could have. And the wormhole looks big only because it's close to us. We're very close to it. The wormhole is only a few kilometers across, whereas Saturn is huge, much bigger than the Earth, but it's far away, and so they look like they're about the same size. I'm now going to show you a movie of what it looks like to travel through this wormhole. This is a movie produced by Oliver James and his team, and Eugenie von Tunzelmann and his team and her team at Double Negative, and I will explain about the movie after you see it. But this is a real trip through that wormhole. This is the wormhole that appears in the movie, and we will watch what it looks like. So we see two images of Saturn. Saturn, as I say, is far away. The wormhole, we're close to the wormhole. Light traveling around this side of the wormhole produces that image of Saturn. Light traveling around the other side produces a highly distorted image of Saturn. So you see two images. And we're going to go through the wormhole. You can watch how the images outside the wormhole change as we enter the wormhole, but also watch how the nebulae and so forth that are on the other side of the wormhole, how they change. So there's no music to go with this. This was just a movie that they made just to see what it would look like. And so we're now going down. The images are pushed off to the side because we're getting close to the mouth of the wormhole. We're entering the wormhole. We've traveled through the wormhole. We're on the other side, and it's the trip is finished. Now, wasn't that exciting? When the movie filming was finished and it was being combined with the computer graphics, Christopher Nolan telephoned me and he said, "We have a problem. Would you come over to my house and let's discuss it?" He showed me this movie and several others, and he said, "This is not exciting enough for Interstellar. What are we going to do?" And I said, "Well, you change the shape of the wormhole until you get something that is satisfactory." He said, "I've done that," and he showed me some more. And none of them were satisfactory. And I said, "Okay, you use artistic license." This is the one place, in fact, in the movie where it's not scientifically accurate. It's based on these equations. And so you will see in the movie then what the trip looks like. When you watch it in the movie, there comes a point when Cooper, played by Matthew McConaughey, is ready to enter the wormhole. He pushes a joystick. He pushes a stick to enter the wormhole. Everything before he pushes the stick is true. It's based on solving the equations for light propagation around a wormhole. It's just the way it would be. The moment he pushes the stick to enter the wormhole, artistic license has been taken. And you see things like this, which are not what was produced by the computer graphics. So the one place in the movie where there was a big deviation in order to make a great movie, abandon the real science. It's the only place where there was a big a change made. However, if you want to know about all the other places where something a little bit different from the real science appears, at least all that I was aware of at the time I wrote my book about the science of Interstellar, you go to my book about the science of the movie. In the back, when I write books, I like to do something like this. You hide secret things in the book. And so in the back, you go to the subject index, but you don't look up a subject, you look up Christopher Nolan in the subject index. And then under Christopher Nolan, you find an entry in the subject interest index, compromises with the science that Christopher Nolan made in order to make a great movie. And you'll find all the pages where I describe the compromises that were made. And as you will see, they were very small compromises in almost all cases. This was the one big compromise. So, do wormholes really exist in our universe? Probably not. The problem is that the walls of the wormhole tend to collapse on themselves and pinch off so nothing can travel through unless you thread through the wormhole something that repels gravitationally. We call this exotic matter. We know that exotic matter can exist in the universe. It's been built in the laboratory. It's, in technical language, it's matter that has a negative renormalized energy density due to effects in quantum field theory. Okay, you can ignore that. If you're not a physicist, you can ignore those words. But it does exist, but we are fairly sure that you cannot get enough exotic material inside a wormhole long enough to hold a big wormhole open so you can't travel through it. However, I spent a lot of time in the early 1990s trying to prove that that was the case, and I failed. And a number of other physicists have tried over the years, and they have also failed. And so we don't know. It may be that wormholes can exist. We just don't know for sure. They are speculation, and so I have this S up here for speculation. But interstellar travel is unbelievably hard by other means, and so we used a wormhole in Interstellar since we can't show that it is wrong. It may in fact be allowed. Black holes, by contrast, do exist. Black holes are truth. We have lots of observational evidence for them, even before we discovered them with gravitational waves. So a big T up here in the right. Black hole looks like a wormhole that is pinched off. It has a singularity down in the center. You can't go through to go anywhere. You fall in and you hit the singularity, and it's rather unpleasant. And I will return to this in a few minutes. So nothing can escape the surface of a black hole. It has a horizon where gravity is so strong that nothing can get out. What does a black hole actually look like? Well, we figured that out in the same way as we did wormholes. So if you have a camera sitting here, an IMAX camera, and a star over there, and this is what the black hole looks like as seen from the fifth dimension. The horizon of the black hole is down here. That point, the singularity, is down below the horizon. I'm only showing it down as far as the horizon, the surface of the black hole. A light ray from the star can reach the camera going around the left-hand side, but it can also go around the right-hand side, or it may go down, go around the black hole once and come back out. So as you see, you could have many images of the same star. And in fact, you can have images be born in pairs and collide and annihilate in pairs when they're all images of the same star. And so the team at Double Negative did some images of this sort that don't appear in the movie, and we actually explored this phenomenon called gravitational lensing. And this then is a film clip from my collaborators at Double Negative. If you look around here, this is what is called an Einstein Ring. In there are images created and destroyed, but it's easier to see it in an inner Einstein ring down here. If you look closely down in here, for example, you will see suddenly something goes bright where there was nothing previously. Two stellar images are created. They travel apart. One of them goes around and annihilates against another image, all produced by the distortions due to warped space-time around the black hole, and really rather beautiful to watch. So if you just look down in here from time to time, there was a pair was created. And it's really quite beautiful. So the camera is just orbiting around and around this black hole, and you're seeing the marvels of what warped space-time does to the images of a bunch of stars as you orbit around and around. And it really is quite spectacular, especially if you don't have any lights on in here. But they wanted lights on so we could see each other. But that's not what you see in the movie. This is what you see in the movie. This is the black hole Gargantua as seen in the movie, and it looks very strange. But it has become the iconic image of a black hole, both for astrophysicists and for the general public since the movie Interstellar came out. So how do you understand it? Well, the black hole Gargantua in the movie has a disk of hot gas around it, much like the rings of Saturn. There's an IMAX camera here that the light is coming to. And light off of the back face of that disk, due to the warping of space and time, it travels up over the top of the black hole and down to the camera, so the camera thinks the top back face is up here. So that explains this piece of the image. That's the top of the back face. Similarly, a light ray from the bottom of the back face goes along that path, so the camera thinks the bottom of the back face is down here. That explains this part of the image. And then light from the front part of the disk goes up to the camera directly, which explains the crossbar part of the image. So it's very simple, very easy to understand, but that's what a black hole with a thin accretion disk around it would really look like. There is a project called the Event Horizon Telescope being done by radio astronomers to make similar images, real images, of a big black hole that's at the center of our galaxy. And it will have success in the next few years. The images won't look quite like this because it is believed that the disk around that black hole is very puffed up instead of being flat and thin. But one of the things you watch for in astronomy over the next few years is the first images from real astronomical telescopes. It's a set of radio telescopes spread over the whole world, combining their data, of the accretion disk around the big black hole at the center of our galaxy. It will be really a fabulous discovery when it comes, and it will be coming very soon. A very important role in the movie is played by Einstein's law of time warps, as I like to call it. What this says is that things like to live where they will age the most slowly, and gravity pulls them there. Isn't that where you would like to live? And so gravity pulls you to the place you will age the most slowly. And that, in fact, explains the gravity of the Earth and the slowing of time on the surface of the Earth. The Earth's mass warps time. It slows down the rate of flow of time on the surface of the Earth. And that time warp produces the gravity that holds us here. And so this was actually verified experimentally in 1976 when NASA flew an atomic clock built by Robert Vassaux at the Harvard Smithsonian Observatory in Cambridge, Massachusetts. Flew it to high altitude in a rocket, and it sent radio signals down, sending the ticking rate of the atomic clock up here down to the Kennedy Space Center, and the ticking rate was compared with the ticking rate of clocks on the surface of the Earth. And indeed, the prediction was verified to the accuracy of the experiment. 1 part in 10,000, 0.01% was the accuracy of the experiment, verified beautifully. The time slows down on the surface of the Earth by 1 second in each century, 1 second in 100 years. And that was the amount of slowing of time that's required to produce the gravity that holds us on the surface of the Earth. That's not much time slowing. But that tells you that near a black hole, where gravity is far stronger, the slowing of time should be enormously greater. And that's what appears in the movie Gargantua. In the movie Gargantua, there is a planet that is near the horizon, near the surface of the black hole. The planet is called Miller's Planet. And on Miller's Planet, 1 hour there is 7 years on Earth. And this plays a very important role in the movie, as you see. In particular, at the beginning of the movie, near the beginning, Cooper, played by Matthew McConaughey, tells his daughter that he's going out to try to into space, and he's going to go through a wormhole, and he may then, after that, go near a black hole. And by going near a black hole, time for him would slow down enormously, while time for her is continuing to march forward, so that by the time he comes back, she might be as old as he is. And he warns her that that's the case. And so in the movie, you see halfway through the movie, he has just emerged from being near the black hole on Miller's planet. And she, by now, has become an adult woman, a theoretical physicist played by Jessica Chastain, trying to figure out the nature of gravity, as I'll describe in a few minutes. He goes near the black hole again, and at the end of the movie, he meets his daughter. His daughter is now a very old woman, about 90 years old, and he is only a little bit older than he was at the beginning of the movie. And this is a very emotional phenomenon, an emotional phenomenon that has showed 100 million people around the world that time is not the way you always thought it was. That near a black hole, time flows much, much more slowly than it does here on Earth. Gargantua, as seen from the fifth dimension, has actually a shape that Einstein's general relativity predicts is precisely like what I'm showing here. It's a rapidly spinning black hole. The shape of space has this form like that. That goes flat far away, and our universe is this flat membrane or brain up here far away. I remember I've suppressed one spatial dimension, so our universe is two-dimensional in this picture. It's an equatorial slice through the equator of the black hole. And it goes down, and here is the horizon or the surface of the black hole. The coloring shows the slowing of time. At the yellow location, time is flowing at 1% of the rate that it does back on Earth. And at the black location at the bottom, time is slowed completely to a halt. And so gravity, therefore, there has become infinitely strong, which is why nothing can get out of the black hole. Now, Miller's planet has to be very close to the horizon because time is slowed so much. And there was a big question in the minds of physicists who saw this movie: how is that possible? It should have fallen into the black hole. And the answer is it's possible because this black hole is spinning very rapidly, and it creates a whirling motion of space around the black hole, like the whirling of air in a tornado. That whirl of space produces a centrifugal force that enables the planet to stay out through that centrifugal force, even though it's very close to the horizon, so that indeed 1 hour on the planet is 7 years back on Earth. So this spin of the black hole is tremendously important. The size of the black hole is dictated by the next piece of physics that you see, which is a giant water wave on the planet. And from the water wave, whose nature I will explain, one can infer that the black hole is 100 million times heavier than the sun, and its circumference, the circumference of the horizon, is about the same as the circumference of the Earth around our sun. So it's really a giant black hole. It turns out that this is essentially identical to the black hole that's at the center of the galaxy Andromeda, the nearest large galaxy to our own. It's much bigger than our own black hole at the center of our galaxy, which is only 4 million times what the sun weighs. But this one is like the one in Andromeda, 100 million times what the sun weighs. And it is fast spinning, as I said. And so this planet near the horizon, on the side closest to the horizon, the gravitational pull is bigger than on the distance on the far side. And there's also an inward gravitational force for reasons I won't go into, but it has to do with the three-dimensional nature of space. But this is the same difference in force as you have for the gravitational pull of the moon on the Earth. The moon pulls harder on the side of the Earth that's near the moon than on the far side, and that raises the ocean up so it bulges out toward the moon and away from the moon and causes the tides on the Earth's oceans. In the same way, it actually deforms Miller's planet quite strongly. Miller's planet was put into this orbit somehow. It settled into this orbit about 1 million years ago, roughly 1 million years ago, as seen in the external universe. But that's only a matter of about 20 years ago, as seen by the planet because of the slowing of time. And so it is settled down into this orbit, and the gravitational force, the so-called tidal force, is causing the planet to rock back and forth under the pull of the gravity of the black hole. And as it rocks back and forth, the oceans slosh. The water swings back and forth as the planet rocks. And this produces gigantic water waves that you will see in the movie. And the time between water waves is 1 hour. And that goes hand in hand with the mass of the black hole. The mass of the black hole is you can deduce from the time between water waves, but also the strength of the water waves, that they are so big, requires that the black hole have this same size of 100 million times what the sun is. So it's quite nice that you can deduce, knowing some physics of tidal forces, gravitational tidal forces, you can deduce the properties of gargantua directly from what you see in the movie. Now, a very important role in this movie is played by gravitational anomalies. A gravitational anomaly is something wrong with gravity that's behaving differently from gravity than you would ever expect that it should. And in the movie, the gravitational anomaly that you see the most, that is most startling, is when Cooper throws a coin in the air and it always lands on a stripe of dust. There has been a dust storm. When the dust fell in his daughter's bedroom, it fell in long strips that turned out to be encoding information about where he should go to find a NASA facility. So there was something about gravity was encoding information being fed to him. But it's a gravitational anomaly because when he throws the coin into the air, it always lands on this one of these strips. Let's watch it again. Always lands on a strip. It doesn't land in between. So gravity is somehow enhanced in a little narrow region and reduced in a narrow region, enhanced in a narrow region. That doesn't happen. You've never seen that happen. Suddenly this started happening 49 years earlier. And this is something that they ultimately figure out is probably due to a civilization that lives in the fifth dimension that is somehow manipulating gravity here on Earth. And if they can manipulate gravity in a way that we had never seen before to produce gravitational anomalies, maybe that can be harnessed. And so Professor Brand and Murphy Cooper, when she's become an adult as a theoretical physicist, they struggle to understand these gravitational anomalies in order to save humanity from a dying Earth. And these are some of the images of the dying Earth. The problem is there are only about 1 million people left on Earth. Everybody else has died through the various geophysical and biological catastrophes that have occurred. They want to lift the remainders of humanity up into space in giant cylindrical space colonies and carry them to some other world. But they don't have the rocket power to lift that off. And so what they need is to be able to turn down the Earth's gravitational pull for long enough to lift these space colonies up. That's the only possibility to get 1 million people off the Earth. And of course, we would say that's absolutely ridiculous, but once in the movie they have seen these gravitational anomalies, that something is manipulating gravity, maybe they can figure out how to do that. And if they can figure out how to do that, maybe they can turn the gravitational pull down long enough to lift humanity off the surface of the Earth. So that's the story of what's going on and trying to figure that out. On the blackboards in Professor Brand's office, there in fact are 16 blackboards filled with equations. And if you're a theoretical physicist, you can study the blackboards and understand the theory that Professor Brand and Murphy Cooper are working on to explain the gravitational anomalies and to figure out how to control them. Murphy Cooper ultimately realizes that half of the answer is on the blackboards, but the other half, she needs to know the laws of quantum gravity, or in technical language, the effective action that arises from the laws of quantum gravity for gravity in 5 dimensions in order to get the final answer how to control gravity. And the only place she can see to get that information is from inside a black hole such as Gargantua. And so I then come to the climax of the movie. And let me back off and explain with regard to this climax. One of the first meetings I had with Christopher Nolan, he talked about how much he admired the movie 2001: A Space Odyssey, made by Stanley Kubrick. And he especially liked the ending, which is so puzzling. He wanted an equally strange ending, but one that could be explained. And so we spent a lot of time talking about the ending of the movie. And the ideas for it are primarily Chris's ideas, Nolan's ideas, not mine. But it's based on speculative real science, very speculative real science. And in the end, he invited me to explain the ending. And the only way you can really understand the ending is to buy my book and read it. The last 3 chapters, I think, basically deal with the ending. I'm going to give you a quick version of it, a very quick version of it, since you're about to see the movie. This is a spoiler, but many of you have seen it already. And if I don't tell you this, then you'll be totally lost in the ending. You'll be entertained, but you'll be lost. Okay. So Cooper falls into Gargantua. There's a lovely momentary scene when he says, I'm now inside the black hole. I've crossed the horizon. He looks up, and you look out of the black hole. Light can come into the black hole. It can't get out. And so he can look up and see the external universe. But you see the external universe, the nebulae and so forth, inside the accretion disk instead of outside. And the black hole is outside. It's all turned inside out. And I'll let you figure out why that's the case. But this is the way it would really look if you were inside a black hole. And it's really a lovely momentary glimpse that comes again from the mathematical solution of the equations. Inside the black hole, there in fact are 3 singularities inside the black hole. Somehow the third singularity is not showing up there very clearly. But you have to read the book to understand why there are 3 singularities. But Cooper gets caught in something that I call the outflying singularity. This is something which is governed by the laws of quantum gravity, and so it contains the information that his daughter needs in order to figure out how to control gravity, in order to be able to figure out how to lift humanity off of the Earth. And so he and TARS, are a robot that goes in separate from him, but in an adjacent spacecraft. They need to, as they go into this singularity, they need to collect that information about the laws of quantum gravity and bring it back and send it to Murph. He hits the singularity. Just before he hits, he ejects from this spacecraft called the Ranger. And you get a momentary glimpse. The spacecraft has been torn apart by tidal forces. It's rather uncomfortable in there. The tidal forces are getting strong. The computer tells him to eject, 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 because the computer knows that the tidal forces will tear the spacecraft apart. And just as he reaches the singularity, he is scooped up by a vehicle called a tesseract that has been provided by bulk beings who live in the 5th dimension. This is obviously speculative. There's a big S up here. Okay. And then so I need to explain a tesseract. It was Christopher Nolan's idea to use a tesseract. I wanted him to be captured on the surface, on the 3-dimensional surface of a 4-dimensional sphere. Chris said, no, we'll use the 3-dimensional faces of a 4-dimensional cube, a tesseract. So if you take a cube and you go up close to one of the faces and look in, the other faces look like that, and that's the far face. So it looks like a square inside a square if you're up close to a cube that's semi-transparent. In the same way, a 4-dimensional cube, the tesseract looks like a cube inside a cube. And so this vehicle that captures and saves Cooper inside as he approaches the singularity is this kind of a tesseract. Cooper is floating then in one of the faces of the tesseract, a 3-dimensional face of a 4-dimensional cube. And he is carried across in the bulk, in the fifth dimension, across our universe. That's 10 billion light years inside our universe, but it's a very short distance back to Earth up in the bulk. And that's a mathematical property that it goes along with, again, for physicists, the fact that our universe is surrounded by a layer of anti-de Sitter space that warps space so as to hold gravity inside our universe, inside our brain. So end of jargon for the physicists. So he gets carried back to the Earth. The Tesseract docks in the fifth dimension alongside Murph's bedroom. And so you see Murph over here. She's in one face, but in her bedroom where it is docked. And Cooper is in this other face. And he can look at her and see her by light rays that come from her head through the faces of the Tesseract down to his eyes, from her feet up to his eyes, around the sides. So to him it looks like he's surrounded by images of the same Murph, the same daughter, but is seen from different sides. So to him, it looks like he's in the interior and there are 6 different Murphs surrounding him on all sides. And that's the way it would look if you were inside one face of a Tesseract looking at somebody who's in a far face. That's the way it would really look. Christopher Nolan then makes it more exciting. He shrinks the size of those faces, and so the faces are much smaller. And then he makes multiple faces running down here. I don't know whether you can see that very well. It's faded out. Is it possible to turn the lights down in here? Well, never mind. We're going to be out of this very soon. So it turns out there are an infinite series of images of Murph that you see. And so in the movie, you have Cooper. Here is one image looking in the back of her bookshelf. Another image. These are 3 images surrounding Cooper, who's floating in the movie. But this also has the property that Cooper can move through this Tesseract, and he's moving in what for him is a space dimension, but he's moving through time as seen in Murph's bedroom. Now, this is a key to watching a Christopher Nolan movie. Chris's movies are always very puzzling. Inception was, this movie is, Memento was, for those of you who saw these movies. But the secrets to the puzzling things are often present in the dialogue, but somewhere else in the movie. So that you have to go back and watch the movie maybe 6 times to really understand it, or you have to read my book, one or the other. And so earlier in the movie, Amelia Brand says to them, them being the bulk beings, the civilization that lives in the 5th dimension, time might be another physical dimension. To them, the past might be a canyon they can climb into, future a mountain they can climb up. To us, it's not. Okay, so you watch for that dialogue. It comes right after they have been inundated by a wave on Miller's planet. And she is telling you, she's explaining to you what's going to happen in the Tesseract at the end of the movie. And so in the Tesseract, in fact, Cooper, by moving in the Tesseract in this direction, he's moving into Murph's future. If he were to turn around and move back, he'd be moving into Murph's past. But he's always going to the future of time as seen in the Tesseract, in the Tesseract phase he's in. But relative to time on Earth in Murph's bedroom, he can go in a space direction, but time is, he's going into far distant future, seen in Murph's bedroom. And then she goes on to say the only thing that can move across dimensions like time is gravity. She's telling you that gravity can be used to go backward in time. And that's what happens in the movie, near the end of the movie. Cooper pushes on things called extrusions that you see. They look like long strips. And in the process, he is sending gravitational signals through the bulk that are going backward in time to Murph to send her the quantum data. And so he, in fact, and this again is for the physicists, he sees her by light rays that travel through the faces of the Tesseract to him, always going forward in time. But in the interior of the tesseract, in the bulk, in the fifth dimension, there are closed time-like curves in physics jargon, and he can send gravitational forces through the interior. Gravity is the only force that can travel through the bulk. You can send gravitational forces that go backward in time. Okay, so that's the quick version of the explanation in the end of the movie. In the end of the movie, well, the goal was to be able to lift humanity off the earth, and well, you'll see, does he succeed or not? Now, as an epilogue to this lecture in the last several minutes, I would like to describe a piece of the movie that was there when we wrote our treatment. It was there in Jonathan Nolan's screenplay, and when Christopher Nolan came on board, he wiped it out. The movie began in all the early versions with a source of gravitational waves, a black hole going around a neutron star going around a black hole and then being torn apart. Gravitational waves go through the wormhole and out, and they're detected on Earth by LIGO and Virgo. And LIGO and Virgo look at where the gravitational waves are coming from. They look like they're coming from Saturn. And as Saturn changes its location on the sky, the source is always near Saturn. But these gravitational waves are produced by objects that are heavier than the sun. They can't be there at Saturn. The only way they could possibly explain this is there's a wormhole out there. And so this is how the movie began originally. When Christopher Nolan came on board, well, and so these are the gravity wave detectors, the Virgo detector, the two LIGO detectors. LIGO is a collaboration of 1,000 scientists in 80 institutions, 16 nations. Virgo is roughly 200 scientists, primarily Italy, France, Netherlands, and Poland. And so these were the detectors that saw the gravitational waves and for the discovery. Chris said, there's too much science in this movie already. We don't need gravitational waves later in the movie. I'm going to get rid of them so that I can bring the tesseract in, so I can bring more science in. So he got rid of them. And then that was the death of the prologue. And then last September 14, LIGO discovered gravitational waves with the Virgo scientists participating in analyzing the data. So a LIGO-Virgo collaboration. And we announced the discovery in February of this year. It took 4 months to, was it 4 months, 4 or 5 months to be absolutely sure that this was the real thing and to get all the data, all the information out of the signals that we could. And so Christopher Nolan phoned me a few days later and said, would you like to come over to where I'm doing pre-production on my next movie, which is about the evacuation at Dunkirk at the beginning of World War II. I'd like to talk. So I went over and he began by saying he's rather sorry he had removed gravitational waves from this movie. And he began to explain how he could have used them in the movie. And then after about 10 minutes, he said, but there's no looking back. We have to look forward. And so what's done is done. So I'm going to wind up with telling you what it was that we did discover, and then I'll stop. So this is the result of doing the data analysis on the signals that came in. 1.3 billion years ago, well, let me say what you're seeing here. You're seeing two black holes by gravitational lensing that are orbiting around each other. And it's the same kind of gravitational lensing as I showed you previously for Gargantua. 1.3 billion years ago, in a galaxy far, far away, there lived two black holes which were orbiting each other. And as they orbit each other, they created marvelous patterns that an IMAX camera would see if it was up close. Though this simulation is by the numerical relativity team that I'm a co-leader of at Cornell and Caltech. The black holes came together, they collided, and they emerged, producing an enormous power output in gravitational waves. Not much to see optically, but in gravitational waves, at the moment of collision, the power output, the energy being put out in a unit moment of time, that power output was 50 times larger than the power being put out by all the stars in the universe put together. but coming off in gravitational waves, ripples in the fabric of space-time that stretch and squeeze space as they go by. Enormous amount of power. In a fraction of a second, the total energy that came out is what you would get by annihilating 3 suns. Just convert 3 suns into pure energy, put it in gravitational waves, send it off in a small fraction of a second. That's what came off. What did it look like from the 5th dimension? This is what it looked like from the 5th dimension based on these computer simulations. That's the warping of space, like I showed you for Gargantua. The color coding is the warping of time. The arrows are the dragging of space into motion. And we go into slow motion. We will pause it at the moment of collision. And this is now the epoch where all that power is coming out. It looks like a gigantic splashy wave in a big storm. It says, in fact, the storm in the fabric of space-time is seen from the 5th dimension, again by computer simulation, solving Einstein's equations on a computer. And the gravitational waves traveling out of the galaxy in which the gravitational waves were born. This happened, as I said, 1.3 billion years ago, when multicelled life was just forming on Earth and spreading over the Earth, to put it in context. The waves traveled out through intergalactic space, across the universe, arrived at our galaxy, at our Milky Way galaxy, when about 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. That's when this burst of waves reached our galaxy. It reached the Earth on September 14, 2015, when the detectors were just ready to see it. It entered the Earth from the southern hemisphere down near the South Pole, traveled through the Earth unscathed, emerged at the LIGO gravitational wave detector in Livingston, Louisiana, stretching the arms of this LIGO detector and squeezing them in an oscillatory way. And then 7 milliseconds later arrived at the detector in Hanford, Washington in the United States. Unfortunately, the Virgo detector is not yet running, the advanced Virgo detector. We really need it in order to determine the directions of the sources of waves like this. And we hopefully will have Virgo operating by this winter. Those waves then had a wave shape. This is the wave shape with in the raw data, with again for physicists, there's a bandpass put on to wipe out anything below 35 hertz and anything above 350 hertz because the detectors are noisy in there. Other than that, this is the raw data. And at Livingston, Louisiana, at Hanford, Washington, you overlap the data. They're essentially identical. And you then clean the signals up and compare with a simulation done on supercomputers by solving Einstein's equations on supercomputers. That's the red, and the gray is the actual cleaned up signal. It matches beautifully, but by comparing with the computer simulations, you deduce that the initial black holes had masses of 29 times the mass of the sun and 36 times the mass of the sun, so the total was 65 solar masses. The final black hole was 62 times the mass of the sun, so there were 3 solar masses converted to pure gravitational wave energy, and the distance is 1.3 billion light years. Comes from comparing with computer simulations. The future, advanced LIGO and Virgo, when Virgo is online, will also see gravitational waves from spinning neutron stars, pulsars, black holes tearing stars apart, neutron stars colliding, perhaps the cores of supernovae, perhaps cosmic strings created by the inflation of fundamental strings, the building blocks of all matter, we think, inflation to cosmic scales in the earliest moments of the universe. And there will be big surprises, we're quite sure, because every time a new window's been opened onto the universe, there are big surprises. And over the next 15 or 20 years, there will be 3 more gravitational wave windows opened onto the universe. LIGO sees gravitational waves. There's oscillate with periods of milliseconds. There is something called LISA. It's a European Space Agency mission, which will look at gravitational waves with periods from minutes to hours. There's something called pulsar timing arrays, which will see gravitational waves with periods from years to decades. and then a technique called polarization of the cosmic microwave background, which will see gravitational patterns on the sky corresponding to gravitational waves whose wavelengths are nearly as large as the size of the universe itself. In a period of 20 years, it's like opening X-ray, gamma ray, optical, and radio astronomy all within 20 years. And that's what we will be doing over the next 20 years. So this really is the beginning of a revolution in astronomy, a revolution that is going to last, become a tool for astronomers exploring the universe over not just the coming decades, but centuries. And it will produce, we are quite sure, a revolution also in our knowledge of the universe. So that's where we're going. I'll leave it at that, but it is truly exciting to not only have been able to collaborate tightly with Christopher Nolan on this wonderful movie, but also to have the superb scientists working on the LIGO and Virgo project pull off this detection after 50 years of work by Ray Weiss and me. It's their discovery, it's their detection, it's not ours. They make us look good. Thank you.